This is one of the topics we had to skip this year because it was not on the AP test. So we're coming back to it. So this is in the section where we're learning how to test for the convergence of a series. And there are 10 different tests that are commonly used in a beginning calculus class. This one is sort of a test, but really it's a type of series, kind of like identifying a series as geometric and then using the test for that. And this type of series is called a telescoping series. If you go way back, remember there were two questions I wanted you to be able to answer when I present you with a series. First, does the series converge? And second, if it does converge, can we calculate a sum? And there are really only two series, common series types for which you can handle the second question. The first one was the geometric series, and you had that formula for geometric series. And this is the second one, telescoping series. Here's an example of a telescoping series. It has this pattern, and later on we'll explain why it's called telescoping. It has this weird pattern of the terms having two parts. This is a single term of the series, and within the term it has two terms. So I'm using the word term in two different ways, so I'm going to call these parts. It has two parts. Usually there's a subtraction symbol between them. Okay? This is what, you can look at this, pause the video, and you see a pattern to this. Here's an example problem. Let's fix the M. Here's a series given in N notation, and we ask the question, does it converge? And if it does, can you calculate the sum? So let's write this series out and talk about figuring out whether it converges and finding a sum for it. So here is the series written out. And this board will show you the official way to do this so that you understand fully the theory behind it, but then we'll look at a shortcut on the next board. So here's the series written out, and make sure I didn't make any mistakes. 1, 2, 3, 4, 5, and these should be two higher. So 3, 4, 5, 6, 7. Good. Now, officially, the way you determine if a series converges is you look at the partial sums, which means you first look at the sum of just the first term, then you look at the sum of the first two terms, then the sum of the first three terms, and you look at the pattern. And if those partial sums approach a fixed finite value, then the series converges, and that value is called the sum. If those partial sums do not approach a fixed value, then the series diverges. And there are two ways they could not approach a fixed value. They could just increase without bound, or they could wobble back and forth between two values. And I brought this series up for several times, one that goes where the partial sums go 0, 1, 0, 0, 1, 0, 1, 0, 1. That series does not converge. All right, so let's look at this one. Look at the partial sums. And I did not combine or simplify because you don't need to in order to see the pattern. So take a look at this. You should pause the video and look at the whole thing and see if you can see where this is going and understand it. But now I'll explain it. Here's the first term, 1 minus 1/3. Then here's the first two terms. So the partial sum would be the sum of these. And of course we could find the common denominator and calculate it and write it as a sum. But that's not helpful for this explanation. Here's the third partial sum, and at this point, we get to do something. We get to see that we have a minus 1/3 here and a plus 1/3 here. So we see these make a 0 and go away. So the partial sum is what remains in black. All right, now let's look at the fourth partial sum. And now that you see me do that, you should pause the video and do that yourself. These go away, and now also these go away. All right, and you can imagine doing it if you're really a math person and thinking of becoming a math major or professor. You may want to keep going, do a few more, write it out and see the pattern. Even don't do this, see if you can write it out on your own. But what remains here, look at what remains. This one here, oops, switch colors. This term here will never, this part here will never get canceled. There will never be a minus 1 anywhere else. And what else will never get canceled no matter how many terms I write? This one will never get canceled. You can see as you look through this, there is no minus 1/2 anywhere. So what I've circled in green will always persist. And then also, look here. These are at the end. These aren't canceled, but later on they will be. Right? And then you would have more terms at the end. So if you write out any partial sum, you could write out the millionth partial sum. It will always have 4 parts that won't get canceled. The first two, the 1 and the 1/2, that will never ever get canceled. And then these two terms here, the second to last and the last term, they just aren't canceled yet. If you wrote more terms, they would be. But this is what would be in any partial sum. So let's write that out in N notation for the nth partial sum. You always have the 1 and the 1/2 because they never get canceled by anything else, right? They never get canceled. And then you always have these two last terms. And if n is 4, this will be minus 1/5 and minus 1/6. For example, if n is 3, this will be minus 1/4 and minus 1/5. So it's always minus 1 over n plus 1 minus 1 over n plus 2. So now to go way back and think, what does it mean for a series to converge? It means that this sequence of partial sums approaches a finite value as n gets bigger and bigger and bigger. So this is actually the strict mathematical definition of the sum of a series, is the limit of these partial sums as n gets bigger and bigger and bigger. We keep writing this on and on and on, and we see what it approaches. So that, strictly speaking in limit notation, that's this. The first two terms that aren't canceled, plus those last two terms, whatever they may be. And you're finding the limit as n gets bigger and bigger and bigger. Well, pause the video and ask yourself, what's the limit of that as n gets bigger and bigger and bigger? It's 0. Likewise, the limit of this is 0. So when you actually do this limit as if you're in the first few weeks of Calculus AB, you get 1.5. And that's called the sum of this series. So we've shown two things. We've shown that the series converges because the partial sums do approach a fixed value. And that limit, it never actually gets there, right? I could write out 1 billion terms. It would never actually equal 1.5. It just gets closer and closer and closer. That limit is called the sum. And I always like to put, especially when you're first learning this, to put sum in quotation marks so you don't think that's what you get if you add them all up. No, that's a naive approach to the concept of infinity. That's not what infinity means. Infinity in these series involves the idea of a limit. This sum, as we take more and more and more and more and more and more terms, approaches 1.5, but it never actually gets there. It never equals 1.5. All right, now no one ever does it that way. So why did I just do that? Well, I just did that so you could see the theory behind it. And in case you take more calculus, you do have to understand the theory behind the concept of the sum of a series. So by writing that all out, it reviews the idea of a sum of a series. But no one actually does that, at least no students do that, when they're taking a test. You use a shortcut. So let's use the shortcut on this. Take a look at it, pause the video, use what would be, I think, an obvious shortcut. What you do is you just think about it. Okay, you look at it, and you look at that term there. And I'll use colors again. Look at this term. You look at the pattern. You say, will that term ever be canceled? No. So you circle it. Then you look at the next term, and you say, will that term ever be canceled? Oh, yes. I've written enough terms to see that it is. Okay. And the next term, will this term ever be canceled? Well, there's 1/3, 1/4. So you look at the second half of each term. 1/3, 1/4, 1/5, 1/6. No, there's no way this will ever be canceled, so I'll circle it. Okay, what about this part? 1/4. Oh yes, that's canceled there. Okay, then you look at this, 1/5. You look at, so that negative 1/5, okay, that'll be canceled because there'll be a positive 1/5 here, right? That negative 1/6 will eventually be canceled. And so once you see that you're starting to put slashes through everything, you're done, and you look back at what you circled. So see, you circle anything that you know will never be canceled and slash things that you know will be canceled. And it involves some thinking as to which parts will come up later and which won't. But these will follow a simple pattern so that you're never going to have a surprise that down at the 101st term there's a part that pops up that's never canceled. It's not like that. Once you start slashing without circling, then you know that you're done. All right, it's a good idea, I think, to understand, just for vocabulary, why it's called telescoping. It has nothing to do with looking at something far away through a telescope. If you think of pirate movies and the kind of telescope they look through, it looks like this, right? Let's see if I get this right. Something like this. All right, so the pirate looks through this, or the sailor looks through that, and then what do they do when they're done with it? They go like this, right? And they close it, and it closes like that. It collapses. At first it looks really long, and then it collapses to just a smaller part. That's called telescoping. And if any of you hike or use anything with a tripod, you often have what are called telescoping hiking poles. And that means they compress, but you can pull them and expand them out like that. That's what it means to telescope. So telescope is a verb in the English language, to telescope. All right, and then finally, more advanced problem that you run into is to take a series that does not look like a telescoping series. It does not have that pattern of two parts with a minus sign between them, and you force it to telescope. You cannot just take any series and force it to telescope. That's not a thing. But if you have a series of this form, where you have n and n plus something underneath in the denominator, then you can force it to telescope. And here's an example. This series of that form, and you might be asked these two questions. Does it converge? And if so, can you calculate a sum? Well, you don't even need to know it's telescoping to answer that question. It converges because if you multiplied this through, you would see it's in the 1 over n squared family. And that's a p series, 1 over n to the p, with p larger than 1. It's in that family. That's technically called the limit comparison test, 1 over n squared plus 2n. The n squared is bigger and more important, so it's in that family. P greater than 1, therefore it converges. So we can't answer the first question without making a telescope. But for the second question, if you want a challenge, you could pause the video and say, how am I going to make this look like that previous n formula? Right? And the answer to that is you use a technique from integration. If you think back to integration techniques, we used partial fractions. So let's do this with partial fractions. You've done these so many times, I'm going to do it using my shortcut, which is I would write, when I break it into the two parts, 1 over n and 1 over n plus 2. That's a 1, so I know I need a 1 in the numerator. So if I think n plus 2, n. Oh, I need a subtraction sign here to make the n's go away. Then I'd have n plus 2 here minus n. That'll make the n's go away, but I'm left with a 2 on top. So what do you do to make it all turn out to be the same exact expression? You put a 1/2. So this series here is actually equal to 1/2 times n equals 1 over n minus 1 over n plus 2. So you see, partial fractions is not just an integration technique, it's a general mathematical technique to split a denominator so that you have two fractions, each with a simpler denominator. And when we do that, we get 1/2 times this. Well, if you look on the previous boards, we've already done this one. This was exactly the one we figured out on the previous page. So this is 1/2 times what we did on the previous page, which was 1.5, which means this is 1/2 of 3/2, or 3/4. So the sum of this series is 3/4. And there's at least one problem like this in the homework.